Welcome. In the last class we started looking at equations of state. We started out with the ideal gas equation PV equals RT, which we realized was an equation of state, and as we said, an equation of state is something that connects the pressure, specific volume, temperature of a pure substance. Then we said that most gases are real, and therefore we need more accurate representations of those gases than what is given by the ideal gas law, that is PV equals RT. And the first improvement that we saw was the virial equation of state, which we said could be written either in terms of a series in pressure or a series in specific volume. Then we had posed this problem to become comfortable with the use of virial equation and had given you some hints and an initial part of the solution. So, let me present the complete solution here. This was the problem regarding isopropanol, and we said that we are looking at isopropanol at 200 degrees C and 10 bar, and we needed to estimate the volume of the vessel necessary to maintain the above conditions for 1 mole of isopropanol. Therefore, you have pressure, temperature here, you have pressure here, you are asked to find the specific volume or the molar volume for 1 mole, and the virial coefficients in terms of the volume expansion were given, C2 and C3 were given, and then after a couple of hints we went ahead with the solution. I had mentioned that we could start out with just 3 terms in the virial expansion for specific volume, Z equals 1 plus C2 by V plus C3 by V squared. This should work in most cases except when the pressures are high and so on. For our purposes, we said we could write this as this Z equals PV by RT, and therefore multiplying by RT by P on both sides, we have V in terms of V, an implicit equation which would be good for iterations, and this requires an iterative solution. And I had given you the procedure for iteration and asked you to work things out. What I will do now is to present a few more steps and again ask you to work things out, because you need to get a little more comfortable with an iteration process. I am not very sure how many of you have solved problems that had iterative solutions. So, we said that the procedure was to guess a value for V and substitute it into the right hand side and find the value of the right hand side, and this can be compared with the guessed value. One way of comparing is to take the difference between the calculated value and the guessed value, and if the calculated value on the right hand side is close enough to the guessed value, then the guessed value is the needed value. We said close enough, you need to be a little careful, otherwise the calculated value is used as a guessed value for the next iteration, and then you use that volume here, substitute that volume here to find out the right hand side and then compare again, and the process is continued until the difference between the calculated and the assumed value becomes acceptably small. This is where we left off last time. I hope you would have worked things out. If you had some difficulty, please pay attention to what follows. For the first guess, we need to start with the first guess, and where do we get that first guess from? If it is a gas, this equation is valid for a gas, we could use the ideal gas value, whatever we get from PV equals RT, as the first guess. We will not be way off. Therefore, V equals RT by P from the ideal gas equation, and if we substitute the values in this particular case, in this particular exercise, R, as we all know, is 8.314 joules per mole per Kelvin. T was 200 degrees C, but we know that we need to use T in Kelvin, so we add a 273 to it to get 473 Kelvin, and pressure was 10 atmospheres. We need it in a consistent set of units, therefore we multiply it by 10 power 5 Newton per meter squared, and if we substitute RT by P here, the numbers for that, we get the ideal gas, let us say V1 in terms of our iterative solution as 3.933 into 10 power minus 3, 8.314 into 473 divided by, this is 10 power 6. So, 3.933 into 10 power minus 3 meter cubed per mole. Hopefully, you got this if you knew where to look for. Substituting this value into the right hand side of the earlier equation, we had set up the iterative volume equation there, 3.933 into 10 power minus 3 V plus into 1 plus C2 by V plus C3 by V squared. C2 was minus 3.9 into 10 power minus 4, V is 3.933 into 10 power minus 3, C3 was minus 2.6 into 10 power minus 8, and V squared is this. So, if we substitute the values here, we end up with 3.573 into 10 power minus 3 meter cubed per mole. Okay. This is V2, which is the calculated value starting with V1, the ideal gas value. On the face of it, this seems small, but let us consider this further. We need to take the difference between the guessed value, which is the ideal gas value, and the calculated value, which is this 3.537 to 10 power minus 3. In other words, the difference between V2 and V1 in this case, which turns out to be 0.396 into 10 power minus 3. This is 3.96 into 10 power minus 4, which is almost 11 to 12% of this value. That is not acceptable, that is very high. 11 to 12% is very high, is unacceptably large, and therefore, we need to continue the iteration. In other words, we substitute V2 into the RHS, calculate the value and calculate the value of the RHS, that is, then calculate the difference between the guessed value and the calculated value till the difference is acceptably small. For the iterations, it is easier to express the equation in the form of n and n plus 1. In other words, we said V 2 was, we get it in terms of V1 and so on. So, we can generalize that and say Vn plus 1 is RT by P into 1 plus C2 by Vn plus C3 by Vn squared. If we do this, it gives us a nice way of looking at the iterations, as well as to write a program to let a computing device do the iterations for us. We do not have to do it manually, and the iterations can be terminated when Vn plus 1 minus Vn, the difference between Vn plus 1 and the guessed value Vn, is less than an acceptably small value, maybe about 1% or 2% of the actual value. What I would like you to do is, this will converge in about 5 iterations. So, I would like you to take another 10 to 15 minutes and actually work out the iterations. It is going to take some time because you are going to substitute numbers and so on, but it is good to get comfortable with the procedure. Okay, you would have had enough time to do the calculations, see whether you got this value at the end of about 5 iterations, 3.486 into 10 power minus 3 meter cubed per mole. This is when the right hand side value is different from the left hand side value or the guessed value only by a small amount, an acceptably small amount, and thus we have reached the volume of the vessel that was needed, which is actually what we started out looking for in the exercise. Also there was another part to the exercise, that was to find out the variation between the value given by the virial equation, the volume given by the virial equation, and the volume given by the ideal gas. In other words, to find out the percentage difference. So to find out the percentage difference, we take the difference divided by the actual volume, and actually we need to multiply it by 100. We will do that in a little while. For now, V minus V ideal gas, the whole divided by the volume, will turn out to be minus 0.128, and therefore the difference between the volumes calculated using the virial equation and the ideal gas equation is large, it is about 13%, 12.8%. This you should keep in mind. The next equation of state that we are going to consider in this course is called the cubic equation of state. There are many cubic equations, we will probably see one or two. The equations of state that we have considered thus far, which we reviewed in the beginning of this class, which is the ideal gas equation and the virial equation. Okay. These equations describe only the gas phase, which is reasonably general for a pure substance, but they look only at the gas phase. Whereas cubic equations of state have an ability to describe either the gas phase or the liquid phase with equal ease, or they can describe, I will not get into the ease of description, they can describe both the gas phase and the liquid phase. In other words, the combination of P V T, if you know P and T, how do you get V, or if you know P and V, how do you get T, is good in predictions for both the gas and the liquid phase, and it is close to experimental values, somewhat close. And what might be surprising is that you have already seen one of the cubic equations in your earlier classes. I am sure you would have seen the van der Waals equation, which is actually given by van der Waals. The full name is Johannes Diedrich van der Waals. He gave it way back in 1873, and even if you do not remember the name, you may remember the equation. This is P equals RT by V minus B minus A by V squared. Let us call this equation 3.6. Now this cubic equation has the ability to describe the liquid phase because the interactions between molecules are considered in the cubic equations a little better, and the A and B, as you already know in the van der Waals equation, are constants for a given pure substance. Therefore, you would have a table that lists A and B for various different pure substances. There is one that lists at the end of your textbook itself. The constants A and B can be calculated from the critical pressure and the critical temperature values. I hope we can recall what Pc and Tc are. Remember that those are the pressure and temperature values that correspond to the critical point. It was a point in the PT diagram, and it was a point on the curve, the top part of the PV curve in a PV diagram, and that is pretty much the place where the critical phase starts. And Pc and Tc values are available in tables. They are available in one of the appendices in your textbook also, the Smith, Vannes and Abbott textbook. There are values of Pc and Tc, the critical pressure and the critical temperature, that are given for various pure substances. Now let me present this first. This A in the van der Waals equation can be written as 27 R squared, this is the gas constant, R squared Tc squared, critical temperature squared, divided by 64 Pc. We will call this equation 3.7, and B equals R Tc by 8 Pc, equation 3.8. Therefore, the constants A and B can be calculated from the critical pressure and the critical temperature values. Before I make some more comments on that, let me present another popular cubic equation of state, which is called the Redlich-Kwong equation of state. The equation itself is P equals RT by V minus B, somewhat similar to the earlier cubic equation, minus A divided by T per 0.5 into V into V plus B. We will call this equation 3.9. A in this case, excuse me, is 0.42748 R squared Tc per 2.5 by Pc. We will call this equation 310. B equals 0.08664 R Tc by Pc. We will call this equation 3.11. Now, you might be wondering, how did I really write this? Yeah, I did say that you can write this in terms of Tc and Pc. How did people get this so seemingly accurate number 0.42748 and so on and so forth? And that is what you are going to do as the next exercise. The basis for the above equations, that is the basis for the equations that gave you A and B for both the van der Waals equation as well as the Redlich-Kwong equation, that definitely needs to be known as a part of this course. Let me give you how to go about doing it and give you some time to do it, and then let us see what to do. In the, if you recall the PV diagram for a pure substance, pressure versus specific volume for a pure substance, at the critical point the slope is actually 0. What is slope? It is the derivative of P with respect to V, dP dV, that is actually 0. Therefore, you could put dP dV equals 0, and also it is an inflection point. The slope changes from one direction to the other exactly at that point, and that gives you another nice mathematical condition, which is d squared P by dV squared equals 0. So, you have this dP dV equals 0 and d squared P by dV squared equals 0, and you have the equations of state which describe PVT behavior. So, please go ahead and try to get the expressions for A and B using these conditions. Take about 15 minutes to do it, which would be till you would have been able to work those things out, get expressions for A and B. If you did not, or even otherwise, please take a look at chapter 3 in your textbook Smith, Van Nyssen, Abbott. There it would have been worked out in some detail. You would need to fill in the missing steps. We will continue the remaining in the next class.